Good morning. Sorry about that. So I posted the chapter 3 notes that we'll need. I hope to finish chapter 2 today. That's kind of wishful thinking, so we'll see where we get to and then go from there. But so we started 2.6 last day, and we'll just keep chugging along. I'm going to cut a couple of corners, so some of those notes will be kind of a little bit more than what we will do for 2.7 and 2.8, but I mean, it's nice to have anyways. So, but I'll make notes of what you can cut. Review. What did we talk about? So we talked about we kind of zipped through linear functions because we've already talked about lines and what does it mean to be parallel and perpendicular and what's the slope and all that fun stuff. So we already talked about lines. So but what we kind of started that was different last day is we talked about transformations of functions. Right, and so we started talking about, okay, well, if I have y equals f of x, and then if I do plus c, right, then I move up c, up c units. If I have y equals f of x minus c, then I move down c units, right? I move that whole graph up or down by c units. That behaves the way that we kind of expect it to, right? And so, and then what we said was, okay, well, if the constant is being added or subtracted to the x, then it behaves slightly to me opposite of how I would expect it to. So if I have y equals f of x, and I'll follow the handout here, minus c, that shifts it to, so in my mind, if I go minus, I want to move to the left, but it actually shifts it to the right. So just make sure that you keep track of those. Then it moves it to the right c units. And if I have y equals f of x plus c, it moves it to the left c units. Right? So if it's manipulating the x, right, and not just the f of x, then we're shifting horizontally. Okay. And sorry, I just need to rearrange here because it's a little weird. Okay, so so we talked about shifting up and shifting left, right, all that fun stuff. And so then we said, okay, we can do a combination of these things. And what we do, so what's important is that we always start with some core function. So, and that's why it's so important to know what the root of x looks like, what 1 over x looks like, what x squared looks like, what x to the 3 looks like, and that's all from section 2.2. So we have this kind of catalog of functions that we know what they look like, and then we can start there, and then we can build up these transformed functions. So we looked at one example. The key thing is that we always start from the inside. So we always start inside the function, and then we're going to bloom out as we do our transformations. Okay, so we're just going to keep talking about transformations here. So that's the end of our review. Okay, we didn't get that far in 2.6. Let's see here. Okay, so oh yeah, the notes for 2.6 are I think 4 pages long. That's because I want to give you a lot of practice. But just to kind of scroll ahead, if you scroll ahead, as long as you're able to do numbers 7 through 18 here on the second page, those are the exercises that we're working towards. Okay, so all the rest are just, you know, for fun. It's even labeled optional here. Right, and so as long as you're able to do these 7 through 18, which we'll get there and we'll do some, then I'm happy. Those are kind of the hardest ones. So this is like the hardest that we'll get from this section. Okay. So before we can do any of those, we need to talk more about just transforming graphs. Okay, so we looked at this example last day, right, where we start with the root of x, and then we shifted it to the right 3 units, right? And if you did have to graph these, I'm not going to make you graph these, obviously, because we're not in person and that's really hard to do. But if you did have to graph these, say later on when you're doing calculus, then you would take maybe 3 points on this curve because you know the general shape, and then you would shift those 3 points around. Okay. But for us, we're not going to do that because it's hard. We don't like to do hard things. So we can reflect graphs. Okay, so we can reflect a graph. So if you have y equals f of x and you're looking at negative f of x, remembering that y is f of x, right? So if f of x is your y value and then you make it negative, what does that happen? So what does that do? It takes positive y values and makes them negative, right? And so then we're flipping on the x-axis, right? And negative values become positive values, right? So we're turning around the x-axis if you are negating your whole f of x, right? So here, I'll make a note and say, since y equals f of x, negative f of x makes all y values negative, right? Or all positive y values negative, and all negative y values positive. Whereas the difference here is if the negative is on the x, right? So then I'm taking positive x's here and I'm making them negative. So then they reflect around the y-axis, right? So here I'm taking x becomes negative x, right? And so then all the positive x's become negative, but all the negative x's become positive, right? So either way, you have this reflection around the y-axis. Okay. Those are just good to keep in mind, right? And we'll see more of that in chapter 3. So we'll just kind of have it in the back of our minds that that is something that we can do. We can reflect around the x or the y-axis. Now for the shrinking and the stretching, even I have a hard time, and I shouldn't say even because I do have a hard time with graphing. For some reason, my brain just doesn't work that way, and so I have to work at it really hard. And that's fine. That's okay. I'm okay with that. But it is something that I know that I have a hard time with. So if you're finding that you have a hard time with these graphs and these transformations, then that's okay, but you need to work at it, right? So just know you're not alone. So I'm going to skip these examples because they're just itty bitty examples just to kind of help you along. So maybe work through them on your own, just make sure that they're making sense, right? And then we'll do the big questions together. How about later? Okay, so vertical stretching and shrinking. So remember the vertical is up and down, right? And so here, notice that I got a c multiplying f of x. So this c is multiplying y, right? So my y values are being manipulated, my x values are staying the same. So here I'll say in y equals c f of x, the y values are being manipulated since y equals f of x, right? So since y is f of x, right, that's something that you always have to remember, right? So now if y is becoming, so my new transformed y is c times f of x, well, that's c, so times the y value. So that's what makes it shrink or stretch vertically. Now, if c is larger than 1, so there's going to be differences where if c is larger than 1, then that's fine. If c is some decimal between 0 and 1, right, then it's going to behave slightly differently. So if c is larger than 1, then you're going to stretch the graph vertically by a factor of c. So what that looks like is like this. So here your blue graph is the original graph, and then if you multiply it by c, where c is some large number, right, then you get this kind of, well, all your y values get larger, right, either in the positive or negative direction. So here I'll say y values become larger in the positive or negative direction. Oh, that's not my eraser. There. All right. So if you're multiplying by 3, for example, then all your y values go from being themselves to times 3. So then you're stretching it like this. Okay. If your c is between 0 and 1, so imagine 1/2, for example, 0.5. So now it makes sense that, okay, if it's smaller than what it was before, right, you're multiplying your y's by something smaller, so by 1/2, for example, then, so here your blue line is still your original function, then what happens? All your y values become squished, right? To me, again, anything that happens on the vertical, it behaves the way I expect it to. So there's nothing really for me to remember here. It's just that, okay, if I have some multiplier on c, multiplier c on the y values, then it either stretches or shrinks, right? So if you say, I'm going to multiply all my y values by 4, okay, whoop, stretch, right? I'm going to multiply all my values by 1/4, shrink. So here, the y values become smaller in the plus minus directions. Taking some liberties there. So again, when I'm manipulating the y values, it behaves the way I want it to intuitively. Again, so horizontally, it's not quite as simple, or at least to me. So, and there's graphs in here in the notes, if you've got the notes, right? Some examples. So if you have f of x equals x squared here, right, that's that purple line. If you're doing 3 times x squared, then you kind of pull it up like this. And then if you have 1/3 times x squared, remember 1/3 is between 0 and 1, so then it kind of shrinks down. Okay. So we can do horizontal shrinking and stretching. Okay, so notice now that the c is multiplying the x, right? So now my x's are being manipulated. And if c is larger than 1, so again, we have this, we distinguish between c's, so multiples that are larger than 1 and multiples between 0 and 1. We are assuming it's still positive, otherwise it would make a mess. So if c is larger than 1, then you shrink the graph. And for me, that's the hard part, right? So if you're multiplying c, so if you have 3 times x, then what happens? Then you shrink your graph. Okay, so then what happens here? This is the blue line is your original function. And then if you have 3x, for example, f of 3x, then things get smushed like this. And that to me is counterintuitive, but it's what happens. So we remember that. If c is between 0 and 1, right, then what happens is you stretch these x's out. Okay, so here then you get this stretch where the blue line is the original function, and then if c is 1/2, for example, then it gets stretched out like this. Notice that your y values still have the same, so you still have the same range, okay, right? Your maximum values are still, but they've been shifted over on the x-axis, right? But the y-axis is behaving the same. So a little bit tricky, at least in my mind, but it's just something that you have to remember, right? So having all of these, maybe put them, this handout, the 2.6 handout, the first 2 pages, maybe just have them available somewhere so you can refer to them, because it's not something that I expect you to memorize for this term. Usually I would expect you to have to memorize them. That's hard, right? But not this term. Okay, so just have them available, use them, and it'll be good. I'm just going to mention even and odd functions. So an even function are things like x squared. So what makes it even is that you can reflect it around the y-axis. Whoop, catching up here. Okay, so a function is even, and we can prove this, but I'll save it for maybe Calc 1 or something like that. But what you would do, and sometimes I do it and sometimes I don't. So is this function even? Okay, so what you have to do is you have to say, okay, well, I can look at negative x, right? So f of negative x. If I'm able to manipulate it to become just f of x, right? So that negative x is absorbed, then I have an even function. I have an odd function if I do the same thing, but then when I manipulate it, it becomes negative f of x, right? So I can manipulate it to become negative f of x. And graphically, what it looks like is you have this even function if you're symmetric around the y-axis, and an odd function is a little bit weirder because it's symmetric with respect to the origin, and that can be really hard to see graphically, or at least I think so historically it is for most students. So, but that's what it is. So for me, being able to check if it's even or odd by looking at f of negative x and manipulating, that's the easiest way. So we can determine whether a function is even or odd. Yeah, maybe I will make you do it. It's pretty fun. So I'll do an example or two, and then yeah, it's pretty fun. So why not? Do I even have examples of it? I don't think so. No. Okay, then we won't do it. But I'll just write out. So we can determine whether a function is even or odd or neither, right? We can get to a place where neither of these work out by taking f of negative x and manipulating the result until we either end up at f of x or negative f of x or neither. And manipulating the result until we find f of negative x equals f of x, then we are working with an even function, or f of negative x equals negative f of x, then we're working with an odd function, or f of negative x equals something else. Then, of course, it's neither. Just as a quick example, let f of x be x squared. All right. Then what happens? F of negative x is negative x squared, and I've got a page break here, and I'm just going to keep it on the same page. So negative x squared, well, we know if I take the square of a negative number, it just becomes x squared, right? So it's the same as x squared, which is f of x. Therefore, x squared is even. All right, so you just put in negative x into your function, and then you just kind of play around with it to see what happens. Okay. That's more to prepare you for calculus than for this course, but it's good to have seen it, and it is really fun to play around with. Okay, so we're ready to do some actual examples that we'll need to be able to do for the test. So on a test or on an assignment or whatever, it'll give you a function, so some transformed function, and then it'll ask you to pick the correct transformation that happened. It is from a list of multiple choice answers, so they can be really wordy. So just keep that in mind, right? I always find that it's easiest if you actually do it just by hand on your own, instead of trying to read through and trying to convince yourself which one's right. So you do it on your own, and then you pick the one that matches what you found. That's the case for any multiple choice, but especially for these. So let's just have a look here. Let's have a look at some of these functions. We're just going to talk about some of them, and then once we get into kind of the harder ones, then we'll do them, right? But let's talk about 7a, for example, f of x minus 1. Well, then I have this function f of x, right? It doesn't matter what f of x is, but everything's been shifted down 1 unit, right? F of x minus 2. So now we're subtracting 2 from x. And remember, as soon as we're manipulating the x's, then it behaves the opposite. So x minus 2 actually moves it to the right by 2 units, right? So whatever f of x is, notice that here it doesn't actually matter what f of x is. We just have this general function f of x and we're manipulating it. So negative x, so f of negative x, so all my positive x's become negative and my negative x's become positive. That's a transformation I'm reflecting across the y-axis, right, for 9a. What about 9b? Well, I'm multiplying my f of x by 3, and remember, so f of x is my y values, so I'm stretching this thing by 3 units horizontally. And, well, a multiple of 3, I should say, not 3 units, a multiple of 3. Let's do 13a together. 13a. So if you have y equals negative f of x plus 5, and just remember you have the handout, so just use those little boxes that I've given you, right, with all the information. So we always start at the function, and if there's something happening inside the function, then we do those transformations first, right? And so here, this becomes, okay, so I have my f of x, and then I'm taking negative f of x. Remember, that was a reflection around the x-axis, right? Because all my positive y's become negative and all my negative y's become positive, right? So reflect about the x-axis, and then I want to move things up by 5 units, right? So we always order of operations here, we kind of bloom out. So when you start at your f of x, okay, nothing's going on inside, so then you move outside, okay, and then you add the 5, so, and then we're moving things up 5 units. Shift up 5 units. Okay. Let's just imagine for a second here that I give you some sort of curve, and maybe it's something kind of this. I'm not going to label anything, right? So here, this is my f of x. What would my negative f of x look like, right? So here I have to reflect about the x-axis. So this whole thing is going to get kind of revolve around the x-axis here. So then, like this, right? Negative f of x. And then I have to shift up 5 units. So these guys just have to shift up 5 units. And remember, I didn't put any units on here, but let's say, you know, maybe that becomes up here or something like that. Notice that it has the same shape as negative f of x. Things are just shifted up. So this is negative f of x plus 5. A little bit tricky because, I mean, I didn't put any labels on here, so it's a little bit hard to know where plus 5 would be, but that's the idea. Okay. Let's do 13b as well. So y equals 3 times f of x minus 5. So again, there's nothing happening inside f of x, right? Nothing's happening on the x, but we are multiplying by 3. So that means we have to stretch vertically by 3. Stretch vertically by 3. Okay. And then I need to move everything down. So after I've stretched, then I need to move everything down by 5 units, or shift down 5. Okay. What about something like 16a? Okay. So let's do 16a together. Oops, not sure why I labeled it C. That's 16a. 16a is 1 over 3 times f of x minus 2 plus 5. Okay. Just make sure. Yep. Always with the plus minus 5. Weird. So we start in the very center of the function, right? And so I have f of x minus 2. So I need to deal with that first. And then I can bloom out. So here now, first thing I have to do is to shift everything to the right by 2 units, right? So shift to the right by 2 units. Okay. Then, so then I've dealt with f of x minus 2. So now I need to multiply that by 1 over 3. Remember, if I'm multiplying the f of x, so the overall function, by 1 over 3, that means that I'm shrinking on the y vertically, right? So my second step I have in blue here. So we're going to shrink vertically by 1 over 3. So all the y values are going to be 1/3 of what they were before. Y values are divided by 3. Then the last thing I need to do, incorporate here, is the shift up by 5 units. So here, last but not least, shift up by 5 units. So I want you to have a look at the rest of these exercises, right? And you have these solutions, right? And so, so you can work through as many or as few of these as you want, but just make sure that you have a good handle on what these transformations do, right? Even if it's just a general f of x like we have here. And I'll look through the notes here, but I think you can, I'm not going to make you do it. But here, if you wanted some more practice, right, some kind of level up practice, then here you'd have to first identify the function itself, right? So here, if f of x is x squared plus 3, then the core function here is x squared, right? So f of x is x squared, and then we've shifted x squared up 3 units, right? So that's a parabola, and it's been shifted up 3 units. Here in 32, the original function is the root of x, which we've seen is kind of that bowl shape plus 1. So again, it's been shifted up 1 unit. And you can even kind of do something like 52, noticing that if you let the original function be x squared, then this is the same as x squared, but then x minus 1 squared, so that's f of x minus 1, times 2, but then it's negative, right? So then we got to stretch 2, and then it's flipped on the x-axis, and then we move up 3 units, right? So this is a huge transformation, but if you're able to build up to this one here, or 51 or 52, you've got the stuff in the bag, right? So I'm not going to make you do that, but we will tap out at these general f of x functions, right? So if you're able to do all of these 7 through 18, then you're good. So let us go to section 2.7. So 2.7 is on combining functions. Combining functions is really fun, so that's why I want to do it. Let's leave 2.6 behind. Oh. 2.7, combining functions. So what we can do is, if we have, so going back to our core functions, right, from section 2.2, x squared, root of x, 1 over x, x to the 3, all those I consider core functions. So what we can do is we can make new functions by combining functions, and there are 2 ways that we can combine functions. We can combine algebraically or through compositions. So we can create new functions, right? Kind of more advanced functions. So we can create new functions by combining 2 or more functions. So there are 2 ways that we can combine functions, and we'll talk about both of them. So there are 2 ways to combine functions, or at least that we'll talk about here. To combine functions. First one is algebraically. Algebra is just adding, subtracting, multiplication, division, that kind of fun stuff, right? So we can add, subtract, multiply, divide 2 or more functions. 2 or more functions. The second way is, and I guess end bracket. The second way, more fun way, is to compose, and it's called a composition, to compose a function by putting another function inside of it, right? Or we can decompose a function. So a complicated function we can often decompose into multiple little functions, okay? And so compositionally, to match kind of algebraically or compositionally, right, by putting a function inside another function. Putting a function inside another function. So So let's talk about algebraically first. It behaves the way that you expect it to. And so let's just bring it in. And we're also going to talk about the domains of these new functions, right? So your original function, let's call them f and g, they're going to have domains, right? Values of x that they can accept. Now, if I combine these into a new function, that new function is also going to have a domain. So we need to be able to find what that domain is going to be. So first here, let's bring in the algebra of functions. So I'm letting f and g be functions with domains a and b, right? So f has a domain of a and g has a domain of b. So we need to find what a and b are, right? The individual domains. Then the functions f plus g, so I can make this a new function of f plus g, and how we denote it is we tend to put brackets around f plus g because that's the name of our new function, or you could call it h of x if you wanted to. But f plus g of x is just f of x plus g of x. So you're just putting those two together, and same thing here. And so the algebra of functions, it looks exactly like what you want to do, right? So if you want to find f minus g of x, then it's f of x minus g of x. F times g of x, well, that's f of x times g of x. F over g of x becomes f of x over g of x. And notice all along here that the domain has been the intersection, right? So the overlap of the individual domains, right? So here, this is the overlap of the individual domains. A and B, right? Remember this upside down U is and, so it's where they overlap. Okay? So it's all the same, A and B. In fact, it's the same for f of x over g of x as well, except now you have the restriction that, okay, well, g of x can't be 0 because we can't divide by 0, right? And so the domain is still A and B, given or such that, depends on how you want to read this thing. So this read x is in A and B given that g of x does not equal 0. Oops, should be end quote, not a bracket. So that's how you read those. So it's x is in A and B, so it's still A and B, but you have that added restriction of, okay, well, and also g of x can't be 0. Okay? Which, fair enough. We're dividing by g of x, so we can't have that. So there's one, so in general, combining functions is not that hard. But there is one example that I wanted to show you because it's got kind of an extra element, just so that you've seen it. So these questions, and then there's some more practice on finding the domain. So find the domain of the functions. I'll leave that to the reader, as a lot of textbooks like to say if they don't want to do something. So here, we're supposed to find f plus g, and I guess I'll put it down here. Hey, bigger. So I want to find f plus g, f minus g, f times g, f over g, and their domains, which means I have to find the original domain. So if I have f of x is x and g of x is 2x, what are some values I can put into each of these? Well, these are just, there's no division, there's no roots, so there's no restrictions on the domain. So overall, the shared domain is the set of real numbers here. Let's do 8 together because it's a little bit, has some restrictions here. So f of x is x and g of x is the root of x. First, I need to figure out what the domains are, right? So here, my domains for these, well, the domain for f of x is just all the real numbers, right? And so here, a is the set from negative infinity to positive infinity, right? Where a is the domain of f of x. I'm using the same notation as the definition here, right? So f has a domain of a, so I'm calling this set a, and then g is going to have a domain of b. So then g of x has a domain of b, let's call it, but b is the set where I have to make sure that x is greater than or equal to 0. I'm allowed to be 0, but I can't take the square root of a negative number, right? And so here I'm allowed to be 0, so starting at 0 up till positive infinity. What I want to do is, before I do find these functions, right, I want to find the shared domain, because remember, the domain for all these combinations here is a and b. So it's going to cut down on some time if I just find a and b right away. Okay. So a and b is the overlap of negative infinity to infinity and 0 to infinity. This one, it's pretty easy to see, right? But I like to do the number line, and then I like to map out my my domains. So if I have a is, well, it's a set of real numbers, so it can be any value here. And then b, it starts here with a closed dot at 1, and then it goes to positive infinity. So then the overlap here is from 0 to infinity. Right. That's probably the easiest way to find that overlap. It's been a long time since we did that, right? We started with sets and finding the overlap at the beginning of the course, and then we kind of haven't done it since. So that's why I wanted a little refresher here. Okay. So then a and b, or if you're able to just look at these sets and find the overlap, that's totally fine, right? But sometimes I find that the visual helps. Okay. So if I have to find f plus g of x, so f plus g of x from that definition is f of x plus g of x. Okay. Well, f is x and g of x is root x. So this becomes x plus root x with a domain of 0 to infinity. Often it is just as simple as plugging in these functions. There often is not any simplification that we can or should do. So, so leaving it as x plus root x, totally fine. Okay. But now notice that I have this new function, x plus the root of x, right? And I know its domain already is from 0 to infinity. Most of the time you would be able to get the domain from the new function, but there are some scenarios where if you cancel something, for example, then it would change your domain. So it's always best to just find the overlap first and then find the function. Let's do f minus g of x. Well, that's the same as f of x minus g of x. What do you know? X minus the root of x. All right, as simple as just plugging it in, and if you see a simplification, go for it. If you don't, it probably isn't there. So the domain here, again, is from 0 to infinity. Fg of x is f of x times g of x, which is x root x. You could probably simplify that a little bit, right, using your exponent laws. This is x to the power of 1, this is x to the power of 1/2. We could simplify this as x to the 3/2, but I'm actually just going to leave it because I'm lazy. And you can too. So the domain here again is from 0 to infinity. The only one that has a little bit of a glitch is if I want to find f over g of x. That's going to be f of x over g of x, right? That's not the bad part. X over the root of x. This one I would simplify a little bit, just because it doesn't look that clean, right? This is the same as x times x to the negative 1/2, right? So let's just simplify this a little bit. X times x to the negative 1/2, and this is x to the power of 1, right? So 1 plus negative 1/2 puts me at positive 1/2, which is the root of x, with a domain of 0 to infinity. But remember, I can't have g of x equal to 0. G of x is equal to 0 when x is 0, right? Because g of x is the root of x. And so I actually need to extract that x equals 0 from the domain. The domain is from 0 to infinity, and g of x. And g of x can't be 0, which means that x cannot be 0. So the domain of this thing is not including 0 to infinity. Right? Often the domain for this last one will change just slightly, right, to extract that division by 0. Like I said before, when we're doing cancellations like this, right, when we end up at the final function, we actually lose that division by 0, right? But we still need to take it into account because how we got there was dividing by g of x, right? So we are dividing by the root of x, so we can't divide by 0 at any point. So here's one of those examples where we've canceled, so we don't see that x can't be 0, right? But from where we started, we know that x can't be 0. So our overall domain is not including 0 to infinity, right? Even though that's not obvious here. So notice that the domain of not including 0 to infinity is not obvious after we cancel and simplify. Okay, so sometimes that'll happen, right? But here, g of x is the root of x, can't be equal to 0, so then x can't be equal to 0, right? So that's the only hard part with combining functions algebraically. Otherwise, you just, if I want to find f minus g of x, well, that's just f of x minus g of x. So how about we take a quick coffee break till 9:05, and then I want you fresh for compositions. Break until 9:05. We're back. All right. Hope you're feeling refreshed. I want to do one more just quickly because the domain, so finding the domain part is a little bit tricky. Then plugging in the functions and dealing with the functions is not that bad. But let's see here. So I want to do one like 13 or 14, it doesn't matter. Let's do 13 together, but notice that they have the same structure, right? So finding the domain of this thing can be a little bit trickier, okay? And I'll show you why. It looks easy enough, right? And it is if you have kind of your absolute values down. But for us, I just want to show you a way to be able to find the domains here. So we need to find the domain of f of x, and we need to find the domain of g of x. And that's before we keep going and find f of x plus g of x, and f minus g of x, and f over g of x, f times g of x, I guess, in there. Right? So first we need to find the domains. So to find the domain of f of x, we need 25 minus x squared, oops, is not equal to, is greater than or equal to 0. Right? The tricky part becomes, okay, the x squared here, right? I know I can't take the square root of a negative number. So that's why I have this restriction that 25 minus x squared, whatever's inside, has to be greater than or equal to 0. That's fine. And so here, right, 25 minus x squared, if I'm dealing with the x squared, then I can move this x squared over here. I can add x squared to both sides. Remember the inequality switches when I multiply or divide by a negative number. So adding x squared is fine. So then I have 25 has to be greater than or equal to x squared. When I take the square root, that's when things kind of go bad, go sour. So because then you end up with the plus minus of 5. So here, right, we could, and I say could because this is not how we're going to do this problem, right? Because we could say 25 has to be greater than or equal to x squared, right? That's true. X squared itself has to be less than or equal to 25. But remember how x squared works. Well, if it takes a negative, then it becomes positive, right? So negative 5 squared is 25, and 5 squared is 25, right? And so I've got this kind of, and negative 4 squared is 16, which is less than 25. And 4 squared is 16, which is also less than or equal to 25, or it's less than 25. Right, but it's hard to see what that value is, right? So what those cutoff points are sometimes. So I want to give you another tool because if you take the square root here, then you get plus minus 5 So here, if you take the square root, it becomes the plus minus 5 has to be greater than or equal to x, but this doesn't really make sense, especially if you doesn't really make sense. If you take a step back and think about it, okay, so x has to be less than positive 5, but also x has to be less than negative 5. That doesn't really, the math doesn't work out. It does incorporate some absolute values, which I don't want to get into because we've left that behind for a bit, and it's not something that I expect you to do. So to be able to deal with this, here we go. Instead, what I want you to do is I want you to say, well, 25 minus x squared, if it has to be greater than or equal to 0, okay, then really what I want to make sure is I can factor this, right? And I want to make sure that I'm always above the x-axis. So here, this becomes the same as 5 plus x times 5 minus x has to be greater than or equal to 0. So now we're dealing with nonlinear inequalities, which was in section 1.8. I was Let's just checking it. Let me just make sure. Yeah. So this is a nonlinear inequality from section 1.8. Okay. So we could incorporate absolute values, which we did introduce in 1.8 as well, but I'm going to avoid that. So 5 plus x and 5 minus x, okay, if I expand this out, I get 25 minus x squared. Fine, great. But so what did we say? Okay, well, I have these roots, right? I've got x equals negative 5 and x equals plus 5, which makes sense. That's what we found up here, are my roots. So that's where things are going to be equal to 0. So if I do a number line, remember how we dealt with nonlinear inequalities? And then we said x equals negative 5 and x equals positive 5 are roots. Oops. Are roots. So at negative 5 and positive 5, and then remember we do test points, right? So this was before reading break even. And we did it on test 1, yep. So where we had, okay, so we've got this kind of 5 plus x and 5 minus x. I only need to know where it's positive, right? Where is this thing positive? So I need to know where a positive times a positive is, or a negative times a negative. So then I take little test values here, and I'm going to split up my line into three regions. Right? My roots are the only cutoff points. And so here, 5 plus x times 5 minus x. Well, if I'm to the left of negative 5, right, so say negative 6, for example, then 5 plus negative 6 would be negative, and 5 minus negative 6 would be positive, right? Which a negative times a positive makes a negative, right? That's not what I want. I want to know, where is this thing positive, right? So here, where is it positive? So then I move on to the next region. So somewhere between -5 and 5, it's going to behave the same throughout here because it's somewhere between the roots. So -5 and 5, I've got our beautiful 0, of course, making it really easy to do these fake calculations, right? And so 5 plus 0 is positive, and 5 minus 0 is also positive, which makes a positive overall, right? And this is the one that we want. So this is a region that we're interested in. We're going to check the third region. And we're going to find that if I let x be 6, for example, 5 plus 6 makes a positive value, and then 5 minus 6 makes a negative value. So that's a negative. So here, the domain for the root of 25 minus x squared is from -5 to +5, including those endpoints because it's allowed to be 0. That's just the domain for f of x, right? So that's why I wanted to show it to you so I could refresh your memories on how to deal with nonlinear inequalities, right? We have to kind of do the number line. You could graph it too, right? And use Desmos instead. You don't need to show me how you found the domain, right? I'll just ask you what is the domain. So if you find that Desmos is easier, right, where you just graph 25 minus x squared and look at where is it greater than 0, that's fine. Okay. Should we talk about transformations just briefly? Only because it's a nice example. So here, if I start with x squared, I know what x squared looks like. And then I have to take the negative of it. So then it flips like this, right? It flips on the x-axis. We know that. And then it's moved up 25 units, right? And so we've got this kind of shape. That's just for fun. So now we have the domain of f of x. Luckily, the domain of g of x is quite a bit easier, right? And so the domain of g of x, equals the root of x plus 3, right? So here, x plus 3 has to be greater than or equal to 0, which means what? Well, if I'm just subtracting 3 from both sides, x has to be greater than or equal to -3. And just always put in your answers, right? If it's greater than or equal to -3 on the number line, something like -2 would satisfy that. -2 plus 3 is positive, right? 0 plus 3 is positive. And let's just take a counter example where x is less than -3, so -4. -4 plus 3 is negative, so that's bad. Okay, so what we have found makes sense. In terms of an interval, the domain is from -3 up to +infinity, including -3. Okay. So in terms of our overlap then, right, our overlapping domain, so A is our first domain, -5 to 5 inclusive. B is from -3 to infinity. So A and B, which is the domain of both of these things together, well, definitely if you want to map it out on a number line, that's great, right? Something like this. So I've got some cutoff points here, -5 and 5, and I have -3. So from -5 to 5 inclusive. And then I have b, which is from -3 to infinity. So the overlap here is from -3 to +5. Overlap is from -3 to +5, right? You're just looking, hey, where is this overlapping? And it's including both of those endpoints. So the domain for the first three of these combined functions is going to be from -3 to 5. Okay? So then a and b is -3 to +5. Okay. Now I'm ready to do these combinations. So f plus g of x, oops, sorry, clean that up a bit. Is f of x plus g of x. I always just like to write out the general version first and then plug in my values just so I can see it. You don't have to, but I do find that it kind of keeps me sorted. F of x is the root of 25 minus x squared plus g of x, which is the root of x plus 3. There is nothing that you can do here to simplify, right? Square roots, you can combine them if you're multiplying, but not, and dividing, but not if you're adding or subtracting, right? So there's nothing you can do here. And the domain here is from -3 to +5 inclusive. F minus g of x is just f of x minus g of x. Same thing, right? Again, if I'm dealing with two roots, I can't combine those until I'm multiplying or dividing. So I just end up at 25 minus x squared minus the root of x plus 3. Sorry, the root of 25 minus x squared. And the domain, again, is from -3 to +5. F times g of x is f of x times g of x, which is the root of 25 minus x squared times the root of x plus 3. Okay. I'm not gonna, okay, I will. I think, so just kind of as a hack, I'm pretty sure that WebAssign would just accept it if you just put it in like this. That's fine. I don't mind that. But we do have the same power here. So by exponent laws, I can combine what's inside under one exponent. So here, recall exponent laws, which say a to the power of n times b to the power of n is the same thing as ab to the power of n, right? I've got a power of 1/2 on each of these. So I can put them all under the same square root, 25 minus x squared times x plus 3. I don't actually see any simplification necessarily, right? This became just more of an exercise in manipulating. That's okay. Sometimes it's worth a shot, right? So what if I take the root of 25x plus 75 minus x to the 3 minus 3x squared? Just as a note, we usually like to have the power is descending, right, in a polynomial. And so here I start with my negative x to the 3 minus 3x squared plus 25x plus 75. But like I said, if you just wanted to put this into WebAssign, I'm pretty sure it just marks it right. So don't worry too much about it. But it was good to be able to manipulate things. So then the domain here, which is definitely not obvious from our new function, right? But the domain here is still from -3 to +5, right? And that would be very difficult to find by this function alone, right? And so that's why if we're able to look at the two functions individually, it's a lot easier. So -3 to +5. Same thing with exponent laws, goes for A over B. So if we have f over g of x, that's the same as f of x over g of x, which is the root of 25 minus x squared. Oops, clean that up. Over the root of x plus 3. That doesn't look like a root, does it? There. Now, if I saw something that I could cancel here, I would, but I know 25 minus x squared becomes x plus 5 times x minus 5, neither of which will cancel with x plus 3. So the best I can do is just combine under one square root by exponent laws again. So this becomes 25 minus x squared over x plus 3, all under the square root. The domain is the same, except now, right, g of x can't be 0 in the domain. So x plus 3 can't be equal to 0. So means x can't be -3. So I need to pull that out of my domain, right? So the domain becomes -3 to 5, including 5, but excluding -3. So I'm going to highlight that here and say this is from up here. All right. So the domain changed just slightly to make sure that I'm not dividing by 0. Okay. So they're tedious, but once you have the domain under control, I think finding the domain of the shared domain is the hardest part, but you only need to do it once and then tweak it a little bit for the division, but you only need to do it once, and then you can just use it for all your algebraically combined functions. So now let's talk about function composition. Okay. So function composition we're actually going to use it in the next section as well. So we'll do a few examples here, but then we'll use it again next day. So, and that's why we have to do it. We have to introduce it. Okay. Okay. So if I have two functions, f and g, right, so just like we had before, the composite function, f, composed with g. So notice here, we've got f, and then it's a little open circle, which is composed with composed with G. So F composed with G is the same as F of G of X. So how I unofficially read this thing is I read this as F of G of X. Okay, so that's going to be helpful. Okay, because what this happens, so what this becomes just from that blurb above is it becomes F of G of X. Right, so here this is F of G of X. So instead of, so in F of X, I'm going to replace all my X's with G of X. In F of X, replace all X's with G of X, which is its own function, right? So you want to be really focused on, okay, so G of X is a function, it's its own thing, and it's going in and replacing all the X's in F of X. Okay? And so unofficially, I read this as F of G, right? I read this little composition dot as of, and that's not true, but unofficially it really helps me because then I read this as F of X. Okay? So here, unofficially, I read this as F of G, right? To me, it kind of makes sense because the O makes me think of, okay, so F of G. And then that's how I get to, okay, it's just F composed with G, right? So here, F composed with G of X is just F of G of X. There is a note about the domain. The domain of these things can get kind of tricky. So I'm not going to make you find the domains, but we'll talk about them here, but I won't make you find the domains. But what's important is that, okay, so F is going to have a domain and G is going to have a domain, right? So before we were just finding the overlap. But now what we need to remember is that, okay, so F is now taking inputs of G of X, right? So G of X has to satisfy the inputs of F, okay? And that's where it gets hard. And we have to look at the domain of G of X. Well, what can go into G of X? And then what G of X is, so what outputs of G of X can go into F. I'm going to bring in that blurb, right? But then I will just say that it can get complicated. Okay, so the domain of F composed with G is all the X's in G such that the output, right, can go into F. Okay. We need all the inputs X to go into G of X. But then we need all the outputs of G of X to be in the domain of F of X. Okay. This can be complicated and it's not something that I'm going to get you to do. Okay. This can be quite complicated. And will not be on a test. Okay, so try it, right? Try to figure out the domain, but just don't worry about it if you're finding it really, really difficult. I'm not going to test you on it. But it will be useful for when you get into calculus, right? At least knowing, okay, it is that complicated thing and something has to go into something, and just kind of knowing what has to happen, not necessarily doing it, is enough for this course. So let's find some compositions of functions. All right, so what you'll find, just as a sneak preview here, is I can give you two functions and we can find f composed with g, or we can find g composed with f, right? So now I'm putting f into g. I can put f into itself and make a new function, f of f, right? Or g of g, right? So there are all these different combinations, which is what we're talking about, right? Compositions. There are all these different compositions that we can make, and here they are asking for their domains. I'm gonna kind of skirt around that. Or I would argue what's more important to take away here is if you're able to decompose a function, right? So a complicated function into multiple small functions, that's going to be really useful. And then I've got it labeled as optional here, but you can absolutely do the same thing with more than two functions, right? F composed with G composed with H, so H is going into G, and then G of H is going into F, right? And so it's this kind of chain reaction. Of course, it's optional, so we're not going to go there, but let me grab some of these here. Okay, so, and their domains. I'm going to skip that here. Okay. So, okay. We're going to find all these different combinations. So F composed with G, G composed with F, F composed with F, and G composed with G. Now, let's see here. The first one I want to do is maybe something kind of cute like 48. So if I have f of x is 6x minus 5, and g of x is x divided by 2. Okay. First thing I'm going to do is I'm going to find f composed with g of x. Okay. F of g of x, right? So I always like to write it like this, right? But really what I am finding is f composed with g of x, which I'm rewriting as f of g of x so that I can rework it. Now, there are kind of two ways that you can do this, right? So f of x is 6x minus 5, and g of x is x over 2. So if you want to plug in g of x first and then do the f of x, that's fine. Or if you want to write f of x first in terms of g of x and then plug in the g of x, that's fine too, right? And so here, there are two ways to find this, right? The first one is to say that it becomes f of x over 2. Okay, so then I'm plugging in g of x into f, okay, where f of x is 6x minus 5. Or I can say that this is the same as 6 times g of x minus 5, right? So notice here I'm just replacing x with g of x. Or here I'm replacing all my x's with x minus 2 in f. They're doing the same thing. We're going to end up at the same place, but just do whichever one comes more naturally to you. Right? Don't try to train your brain any other way. But so that's why I'm giving you both options, and just do what feels right. So f of x minus 2 is 6x, x over 2, not x minus 2. F of 6x over 2, oops, not behaving today, minus 5. Okay. Or the other method, I have 6g of x, I'm replacing with x over 2 minus 5. Notice that we get to the same place. We arrive at the same result. So it doesn't matter how you do this, right? We find that f of g of x, which is actually f composed with g of x, becomes, regardless of how we got there, 6 times x over 2 minus 5. You probably want to simplify this a little bit, right? And so notice 6 over 2, I can simplify to 3, so I get 3x minus 5. Okay. We're going to skip the domain, but I do want to talk about it just briefly, right? So here, what it means is, okay, so the domain of f of x, I can put in any value of x here because there's no division and there's no roots. So I've got negative infinity to positive infinity for x. Same thing here, x over 2, even though there's division, but the x is not in the denominator, so there's no restrictions on x. Any number can be divided by 2 and we can still get a number. Right, so both of these have a domain of all real numbers. Okay? So no matter what g of x is, right, so no matter what x is, and then I divide it by 2, I can put that into f of x, there's no restrictions. So the domain here is still negative infinity to positive infinity. But it gets a little bit tricky. Okay. G composed with F. Let's do that one. Okay, do it a little bit quicker this time. G composed with F of x is G of F of x. Now, I kind of jump back and forth between these two methods. So just remember, you can do either one. Right, but what I'm going to do is I'm going to write out my f with g of x and then put in my g of x. Or rather, write out my g of x. So that's going to be f of x over 2. Right, g of x is x over 2, but now I'm replacing my x's with f of x, which is going to be an f of x was 6x minus 5, so 6x minus 5 over 2. I don't really see a way to simplify this thing because 5 is divisible by 2, so I would end up with a fraction again, right? This is a linear function. So I rearrange y equals mx plus b. So I have this new function from these two old functions, 6x minus 5 and x over 2. So now I've made a new function, and that's what we're doing here. How about f composed with f of x? Well, that's the same as f of x. Okay. So in 6x minus 5, I'm going to replace my x with f of x. So 6 times f of x minus 5. but f of x is 6x minus 5. So you really want to keep your focus here and just, so f of x is going in and then f of x is its own thing. So 6 times 6x minus 5 minus 5. This I can simplify, right, a little bit. So I get 6 times 6, 36x minus 30 minus 5. So I get 36x minus 35. How about g composed with g of x or g of gx? G of x is x over 2, so I have g of x divided by 2, and then g of x is x over 2, so I have x over 2 over 2. This is a fraction over a fraction, right? If you imagine 2 over 1, x over 2 over 2 over 1, I have to flip and multiply, right, to simplify this fraction over a fraction. So I get x over 2 times 1 over 2. Putting me at x over 4. So now I have a new function, right? Composition of functions. Let's do I want you to do 56 on your own, and then we'll do it as a review next day, right? So try 56 on your own. Try 56 on your own. And we will use it as review next day. Oops. If I could spell review. So try 56 on your own. Try a couple more because this is tricky. And like I said, we need it for the next section as well. So let's just get it under control and then we'll be good to go. All right. So if you have questions, let me know. Otherwise, I'll see you on Thursday. Stop this here.